The students, you may recognize this from the Atlas lab. What we're doing here is building pendulums. So what I have is a mass. This is 200 grams at the moment. And we're going to fix it to a string. I'm going to be careful how I fix it so it doesn't fall off. And what I'm going to do is to fix it directly to the string first. And then we're going to set the length. So this is what we mean by constructing a pendulum is you figure out how long you want the pendulum, and then you attach it. Now, I want mine about half a meter. So we're going to measure out about half a meter of string. And I want it half a meter from the center of mass of our pod. Right, so measure there. There's the end of our rule. That's about right. And a little bit extra. And we just attach it to our stand. And then the excess, we're just going to get out of the way. So this is going to be important when we want to change the length. Now, nothing that we're doing here is crucial. I do not have to have this exactly the right length. But I need to have it constant. So right now, I have this, and I'm going to do all the measurements with the amplitude. That's the first thing we're going to check. What do we mean by amplitude is how much we pull it back. So here, it's resting nice and stationary. I'm going to pull it back, say, 10 centimeters, and let it oscillate. Now, in the lab, you have that there is, get in front of the camera, degrees, 5, 10, 15, 20, 25. You can use trig to figure out how far you have to pull it back. And that's what I'm going to do. I'm going to pause the video for a minute, and we're going to do that. So one measurement is how much we change the amplitude. We're not going to change it much because if you go too far, then we know that the amplitude will depend. Right? Because you're not the first people to do this experiment. And the other part is that we also know that there's this issue with the whole stand moving. So we're going to try to keep the oscillations manageable. But really, everything we're talking about with pendulums, we're making an assumption that the oscillation is small, that there's not a large change in amplitude. And that's because this thing's moving in a circle, so it should have 10 trigonometric functions associated with it. Right? The motion of this thing should depend on sine of the angle or cosine of the angle in some way. And we're assuming it doesn't. We're assuming what's called the small angle approximation. That it actually just depends on the angle. So we're going to carefully set this up so that we have the correct length and the correct weight, and we're going to, off camera, figure out what length we need for this and do the amplitude. Now, the next thing we're going to do after that is, I have my mask on. It's been a work day. Hopefully, when you see this, having the masks will be just a necessity, not like, oh, you also need a tank of oxygen or something. Or, we're not in the apocalypse, or just in normal. We can also change the mass. All right, we can have 2 masses going. I'll actually change the mass physically. It'll be, we can go up to a kilogram if we want, but I believe the lab doesn't ask for that much. We'll go small masses and big masses. And we can also change the length. So we're going to be very careful. I'm going to pause the video and actually set it up. And what we're going to do is time the oscillations. So from the camera's perspective, it's when it crosses the bar, but the period is not each time it crosses that bar. It's each time it crosses it, say, right to left. So start, stop. All right, that's one complete period. We're going to time 10 of those. So when you get your time off of the timer, you're going to divide by 10. And that'll be the actual period. And we do that so that we're not factoring in the time that I have to click on the thing out, does that take me half a second or not? So we're going to be careful. We're going to pause the video, do the calculation, set up, and do the measurements. Okay, so I don't know if you can see this, but we did make one subtle but important change. Oops. We have two strings. This one, it that keeps it from giving us too much difficulty. So here is our setup. Hopefully you can see that. I'm trying to keep as much stuff in the video as I can. From the bottom of the pivot, so that's where the string is constrained, to the mass, to the center of mass of the weight, is about 50 centimeters. So what that means is, beforehand, I figured out exactly how much I needed to pull each thing back for each thing. So when I say 5 degrees, it'll be 4.4 centimeters. And when I say 10 degrees, it'll be 8.7, and so on. So I'm going to time it. I'm going to pull it back a certain amount. I'm going to use, this will be upside down a bit better. And you can see the amount of air. So this is very approximate. So we're going to start it oscillating, and then you'll hear me say count or start or something like that. And then we'll count 10 of these. Start. Nope. Do it again. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what I got was 14.2 seconds, 14.19. I didn't like that. So what I'm going to do is when it gets to the leftmost extreme, that's when I'm going to start. All right? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 14.2 wasn't bad. I got exactly 14 seconds. Hopefully you can see that. There's a lot of glare in the room right now. So, okay. So we're going to do it again, but we're going to instruct it more. So we'll be writing this down as we go. For a very small, for 5 degrees, the total time was 14 seconds. For one oscillation, it's a tenth of that. It's 1.4 seconds. Okay. So we're going to do a medium oscillation. And what we're going to do is get it started. So I need to pull this back 8.7 centimeters from equilibrium. And let it go. A little bit more, and it's going to go for a while. All right, I'm going to reset, and again, leftmost was when I started. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.04. So we basically make that 1.404 seconds. So we're going to keep doing that. We got 15 more of these to do. So this time, for 15 degrees, we got to go 12.9 centimeters. Right. And again, these amplitudes are approximate. They should be getting larger and larger as we do this. So again, leftmost is when I start. Clear? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.22. So the period for that is 1.422 seconds. And we probably notice a bit of a trend here is approximately 1.4 seconds. The error in timing might be down to the 10th of a second. We might not be able to get any better than that. Or it could be that it's going up because it has increased every single time so far. So the next two, that's why we keep doing more data. So we'll do 17.1. Again, it needs to be a slightly larger oscillation. And then again, when it goes to the left, that's when we start. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.13. That's 14.13. So that's kind of killing it goes up constantly. But can't be certain of that is you can't compare two data points themselves. You need to have several data points. You need to have lots of data to tell you if there's actually a trend or not. All right. So we're going to go to 21.1. As I move it up slightly. Because we're basically building size of the triangle. Okay, so there it goes. You might think, well, what if it slows down? If, it's not apparently slowing down very much as we do this. So we'll see how this goes. So start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.29 seconds. 14.29 seconds. That is a period of 1.429 seconds. So, thus far, it seems like maybe it goes up, but I want you to ask these questions when you have all the data in. It's not just that small little bit of change in the hundredths of a second. It doesn't change over whole seconds or half a second at a time. So this was 200 grams. So you can reuse that. Where it says 200 grams, you can just copy your numbers over. We're going to take the small amplitude here, and we're going to say that was 14 seconds and 1.4 seconds for one period. All right, so 14 for 10 and 1.4 for a single period. Now, we can go down to other weights. We'll get 50 grams out. Here's our 50 gram. Let's hang it there. And we're going to pull it back to about the same amount. And instead of, okay, so here's the thing. I'm just going to claim that the amplitude doesn't matter. I'm not going to be very precise on this. I'm just going to get it going. Because we'll see later what actually does matter. All right, I'm telling you ahead of time. The amplitude on this short approximation, small angle approximation, doesn't matter. So here, we're going to do the mass changes. This is the 50 gram. All right, so we're going to time it. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14 even. So I know sometimes you're probably doing a lab and you're like, how did these numbers come out exactly the same like this? It's fluke. It just happens. So, I mean, they should vary a bit, but it's okay if you're doing this and you're getting exactly the same numbers, because it can just be the timing of it. Right? It requires me to see and not be watching the video, but actually be watching the object oscillating and time it correctly and react to it. So we're going to do the 100-gram mass instead of the 50. We've already done 200. This is the 100 again, and we're just going to pull it back a little bit and let it go. All right. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 13.97. So 1.397 for the period. You can probably guess that the mass doesn't matter either. However, we're not going to, maybe small masses don't matter, but big masses do. So here's our big mass. I'm going to let that go. So we're going to clear. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's odd. It makes me think I didn't count right. 14.72. But we're going to do it again. We're going to make sure that we didn't have a big outlier. It's basically the same. Ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 14.5, and I'm okay with that. Those aren't very big changes. Right? I mean, we can certainly do a kilogram. This is not on your list, but you can do it if you like. I will say one other thing is happening. Note that the size of the mass changes as we do this. Certainly, the center of mass is changing, so the length is slightly changing. So I expect this to get a little longer as well. We'll just quickly do this one. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.78. So that's forecasting that maybe the length matters. We're not going to use a kilogram because I don't want this thing to start swaying as we do this. So when we do the final bit, it says to use 500 grams. I'm not going to use 500, but I am going to use 200. The mass effectively doesn't matter. But I'm going to be very careful to pull it back to the middle amount of mass. But now we got to measure every time the length of this thing. We're going to start with 40 centimeters. So, and I'm going to do it from the center of mass of the weight. So, I don't know if this comes through on video. That's about, go more. That's I'm happy with. So there is a to securing these things so they don't move very much. So this is 40 centimeters. You can't quite see that, can you? There we go. All right. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12.75. That is, where is, I'm looking at, so my image is on a monitor and it's weird. 12.75. So the period is 1.275 seconds. So let's see. We're going to go the same way, 60 centimeters. So let me slip the length of this off. There's 60 centimeters. There we go. All right. So I may have to be careful that this doesn't hypnotize you unless you're watching it. Start. Nope, I don't like that. That didn't work. I didn't. All right. Start. Hit the wrong button. 2, 3, 4. Yeah, I'm not trusting that I hit the right button there. I'm going to start again. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You should always make sure that if you see a problem with the experiment, you stop it. Don't just sit there and be like, yeah, it's a fine, because it's probably not. 15.6 seconds. So 1.560 seconds for the period. That's what I meant, is over 10 oscillations, the changes should be appreciable. They should be on the order of seconds. Periods should be going up large fractions of a second, not very small fractions. So we'll do 80 centimeters now. This is the one that's always fiddly, but it has to be done. Because if you're seeing it, seems like the length matters. And if you're reading right below the block, it tells you what the formula is. So you kind of know. I'll tilt this back down. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 18.09. 18.09. So we're going to do 1 meter now. If you've seen grandfather clocks, their pendulums are about 1 meter. They're not quite, because what At this point, we know about moment of inertia. What matters is the length that goes into the moment of inertia formula, not the overall length. It's basically, it has an approximate length. Right? You know, if you've seen roundabout clocks, they got these big constructed pendulums, which are there to make sure that the length can be adjusted and the temperature doesn't affect it, and all sorts of stuff. So you can see that is about a meter. And none of these have to be perfect. But there's a reason why the pendulum in a clock is about a meter, is because it should take out exactly 2 seconds. Well, actually, if it's 0.994 meters, which this probably is erroring close to, and it should pick out a swing every 2 seconds. I start sounding like those people on YouTube that talk in weird voices. So it started going. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 20.19. So the period is 2.019 seconds. 20.19, 2.019 seconds for the period. All right, so now we need to do 120 centimeters. That means I need to make some slight adjustments here. I need as much of this string as I can get. So 120. I also need my 2 meter stick. Do I have a meter tape? I should have a meter tape. Here we go. Here. This is going to be approximate. There's our 120 centimeters. Let's get our math. This is why you guys work in groups, aside from the fact that we don't have equipment, it is fundamentally hard to get the right amount of stuff set up so anything can be done. And I don't have enough string, unfortunately. So we only get to 1 string here, but it shouldn't be a problem. The oscillations are going to be fairly gentle. You may see some weirdness. That's okay. This is making sure the string stays out of the way. Could have maybe tied this to adjustable length, but I don't trust it. I just trust to keep the string out of the way. So there's our pendulum. Now it's below the table. And it's in one plane. You might wonder, hey, does that affect anything? I don't know, maybe. But I don't think so. Not over 10. If it's going to be a problem, it's going to be when I do something like push it in a big circle. I'm just going to let it release. But it should be okay. All right, so hopefully you can see that when it reaches over here, hopefully you can see the motion, but it is a little bit, actually, let's see if we can't. There we go. That's about it. So still going to be visible, still swinging. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 21.81. 21.81 or 2.181 seconds for the period. So I think it's clear that in our data, for the length, it ran from 1.2 seconds to 2.1 seconds. That's a significant change. Whereas for our mass and for our amplitude, those were not significant changes. And so what seems to matter to the period is the length. Now the other thing that matters is the acceleration due to gravity, right? Because of what's going on here. In this pendulum, we have, let's stop it here, there's a tension which runs along the string, and there is a weight force which is straight down. So there's a couple different ways I could vary G and confirm G matters. One is to build a rigid pendulum that can oscillate on its side, so that it oscillates kind of like that instead of straight up and down. It oscillates kind of maybe like that instead of straight up and down. The other thing I could do is send the pendulum to the moon or to Mars and see if it ticks out the same time. We're obviously not going to do that. We're actually not going to do either one of those. We're just going to tell you straight up that the period of the pendulum has this functional dependence here. Focus. The period should be, there we go. The period should be 2 pi square root L over G. Now on the very last bit of the lab, what we ask you to do is take this length data and presume you don't know G, but you could measure the length and the period correctly. Plug the length and the period in and calculate what G is. And if you do that, yeah, so this is kind of a weird view. Let's go back to the pendulum. So if you do that, then you get a measurement of G at this location. And that's how they measured for a long time the acceleration due to gravity. To an accurate value is that they used long, carefully constructed pendulums, and they carried them from place to place. And so as long as you could figure out what G is in one location, you could figure out what it is at other locations that are removed from it. And so you could figure out like the shape of the land or the density of the stuff underneath. All right, so I ask you to pretend you don't know G and try to figure out what G is. All right. So that's a 35-minute video for pendulums. I hope you have the patience for this, but we're just going to stop it right there.